Hello, Mr. Gasser here, 275. Ellipses, here we go. Calculate an eccentricity. So ellipse is this shape, okay? It's kind of like an oval, but it's called an ellipse. And eccentricity measures how different from a circle an ellipse is. That's key. Eccentricity will always be between 0 and 1, so eccentricity will be a decimal, and it has no units. Okay, so for instance, the eccentricity of this, I'll tell you this is a perfect circle. How much does it differ from a perfect circle? Is 0. That's you 0.000. Okay, like that 0 and a circle look the same. This would have an eccentricity of 0.6 and maybe say 0.600, let's say. That is a measurement, so this differs from a circle quite a bit, 0.6. And the highest it gets, if you keep moving out your foci here, and it gets squished and squished, the furthest that it could get, if basically you draw and it just goes back and forth, would be this. The highest eccentricity it can be is 1.0, and that would be the eccentricity of a line. Okay, this is important. Know this in your head as you go through this. Write the formula for eccentricity in the box below. Hint, reference tables. Where will you find that? You will find that right here. Eccentricity, distance between the foci, divided by the length of the major axis. Distance between the foci divided by length of the major axis of major axis. Okay, so hence this is saying the major axis is from here to here. That's what the major axis is, those dashed lines. And the foci are these 2 points. If you draw these, it is the spot where you put 2 pins and the loop string goes around. That's the foci. Distance between the foci is this. Okay. And then we're going to divide them. So here we go. Calculate the eccentricity of each ellipse below. Please show your math. Express each answer to the nearest thousandth, ladies and gentlemen. This is the sort of standard we use for it, is 3 decimal places. 3 decimal places. Okay. So first we want to do, here's the formula here. I encourage you to write it down. I'm going to save some time here so this video is not as long, and I'm not going to write those down for every single one. So I want to go here. I'm going to measure from the center of one dot to the center of the other dot. So this I got to be, let me see, I'm getting about 4.8 or 4.9. Okay, so I'm going to say it's 4.9 here, but maybe you got 4.8. That's fine. It's not exact. And then that's the distance between the foci, the length of the major axis. It's a little hard for me to, I can't really get my head in there without getting away with the camera. It would be 9.7. 9.7 centimeters. Now, if we go back to glurfing the units, this is what's important, is centimeter over centimeter, right? Centimeter over centimeter is the same as, 7 over 7 or 16 over 16. It equals 1, and therefore what we do, it just kind of cancels out. That's how you have no units. It's just a straight ratio. And then if you were to do that math, your answer is going to be 4.9 divided by 9.7 equals that. Now if I round it 3 decimal places, I look at the 5, and to see if the 5 stays a 5 or becomes a 6, I look at the number next to it, that 1. If it's 4 or below, you let it stay. If it's 5 or above, it will go up to a 6. But it's not, so it's 0.505 is the answer. 0.505. When you do this, always do the math. Show your math below. That's important. Okay, don't just be writing answers. Next page looks like this. Okay, number 5. Okay, and it has the 2 foci there. It has different points on it. The major axis is going to be like right from the center of A to center of B, the way this is drawn. So that will be, from between the foci, I got it to be 2.0. So you want to write 2.0. Okay, don't just write 2, don't just write 5. 2.0, it's exactly that. It's not 2.2, it's not 1.9, 2.0 is the distance between the foci, length of the major axis, 5.5. Again, it's a little hard for me to do this. I can't get my head right over the paper because of the camera. 5.5 centimeters. Centimeters cancel out. Your answer there is going to be, when you round it properly, if those are the numbers that you get, again, you're not copying right off me, 0.364. All right. This one, 6, draw in the major axis on the ellipse to the right. Label it major axis. So this is just, hopefully maybe you can get a ruler, do it nice and straight, is the idea. Do it like that. Okay, that's the major axis from there to there, and label it major axis. Okay. Calculate the eccentricity of the ellipse to the right. So it's presented a little different. And then this is going to be 4.0. So I got 4.0 centimeters is the distance between the foci. And this distance here, I got it. If you want to draw in the major axis, maybe you get a ruler and you should. I'll draw it in. It's not on there. But basically you want to measure between here and here. And you go like this. And that's going to be 8.0. 8.0 centimeters. Okay, centimeters cancel. And if I do 4, watch this. 4 divided by 8, 0.5. Now it's exactly 0.5, so there's infinite zeros that go on. So you want everything to the nearest thousandth. Therefore, your answer is going to be this. To show that it's exactly that, you would go like this. It's exactly 0.500. That is important. Too many kids mess that up. That's important that when it says to the thousandth, you have to put those zeros in there. Okay. 8, also important. Here's the star, and this is the as it revolves around. And it's going to go, I'm going to try to do it. I'm terrible at this, but I'm going to try to do it. The speed, it goes slowest here, slow, 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 speeding up, getting closer, getting faster. Faster, if it kind of whips around, slowing down, slowing down, slowing down, slowest, speeding up, speeding up, speeding up, with fastest, okay, it does that. Therefore, the closer the planet is to a star, the faster it moves in its orbit, because of its gravitational pull is stronger here. So, at which location is the planet traveling fastest? Where it's closest, it's point C. B, at which location is the planet traveling slowest? It would be where it's furthest away, right here, which is point G. C, which of these locations, does the planet have the fastest orbital velocity? So it's going fastest in its speed, B, A, or H. The answer is going to be B, because at that point it's closest, or it's speeding up here to the fastest point. So B is the answer for the fastest orbital velocity. D, which of these locations does the planet have the slowest orbital velocities? Of these choices, B, D, and E. And B and D are kind of similar distances away. This is speeding up. This is slowing down, but it's still probably the same speed. E is furthest away. E is going to have the slowest of those three. And which of these locations is the planet speeding up? Again, this is fastest, this is slowest. So this is all speeding up here, and then from the fastest point here, it's kind of slowing down. So my choices are speeding up, D, E, F, G, H. These are all getting slower. This speed is increasing, it's accelerating, so it's going to be H. Know that. That's a key part of Kepler's law. Okay? Here we go. And now we're on to number 9. Number 9. The eccentricity is, so distance between the foci is, I measured this to be 9.1 centimeters. 9.1 centimeters. And I encourage you to write the formula out every time or some abbreviation of it. And then length of major axis, I get in 10.7. Sometimes I've also gotten 10.6. So either one of those is okay. But just writing 10 is bad. Writing 9, bad. It's not 9 divided by 11, not 9 divided by 10. 9.1, 10.7, 10.6. Therefore, if I was to do 9.1 divided by 10.7 in this case, I got 0.850, and I look here, does that stay a 0 or become a 1? The 4 next to it makes it stay a 0, so it's 0.850. You will have a different number. If you got 9 here, or you got 10.6, you'll have a different number. Okay. What is the eccentricity of Saturn? Hint, Earth Science Reference Table, page 15. Page 15 is right here, page 15. What am I doing? The eccentricity of what? Of Saturn. So Saturn is here, okay, 0.054. Make sure you get that right. Okay, copying that down right, 0.054. 0.054, which is more elliptical, the ellipse above or Saturn's orbit. More elliptical, so that's the ellipse above. This is Saturn, which is more elliptical. More elliptical, okay, not elliptical. This is more elliptical, more like an oval, less like a circle. Okay, the higher eccentricity, the higher the eccentricity, the more elliptical it is. That is a key point. So this number's higher. This is much more elliptical. This is a very low number. So therefore, we say ellipse above. Okay. 12. Eccentricity. We're going to calculate the eccentricity again. Here we go. We're going to do this. what did I get? 7.5, maybe 7.6, but I got 7.5 centimeters. And then the length of the major axis is 11.5 centimeters. 11.5 centimeters. They cancel out. I do 7.5. 7.5 divided by 11.5 is 6. So I look here, 6. This 2, does it stay at 2 or round up to a 3? The 1 here makes it stay at 2. 0.652. Always between 0 and 1. So if you get 1 point something, you did something wrong. Sometimes kids do 11.5 divided by 7.5. Don't do that. Which is more elliptical, the ellipse above or the orbit of a planet with the eccentricity of this. More elliptical. The higher the number, the more elliptical, which means less circular it is. So for instance, just looking at these, this is more elliptical than this one. Okay, because it's more oval, flatter. This is closer to a circle. So therefore, which is more elliptical, it's going to be the planet with the eccentricity of this. Planet with E of 0.864. That's key. And then 14, if the star was at point A, so here's my star, I'll draw it in there if I want to. Draw an X on the orbit where the planet will have the highest orbital velocity. Okay, so it goes faster when it's closest, so X, highest orbital velocity right there. Okay, that's key. And then rounding the corner onto the last page, here we go. Eccentricity of this. Okay, what we're doing here is, again, the distance between the foci, 1.0 centimeters. And this is going to be 7.0 centimeters. Write the point O's in there to show it's exactly that. Okay, centimeters cancel out. 1 divided by 7 is.
Please excuse the interruption. Miss Yates, please dial 4002.
Okay, 0.142, and then so the 2 is to stay a 2, become a 3. The 8 makes it become a 3. Therefore, 0.143. Okay, that's the eccentricity of this. And then what's the eccentricity of Jupiter? Again, page 15 of the reference table. That's right here. Jupiter, eccentricity, 0.048. 0.048. So 0.048. So that's a very low number with that point, with that decimal there. Which is more elliptical, the ellipse above or the orbit of Jupiter. More elliptical, less like a circle, higher number. Therefore, the ellipse above. Okay, because that is higher than that. This is what gets weird with the decimals. Students have trouble with it, so be careful. Ellipse above. Okay? If the star was at D, I'm going to draw it in there. Star was at D, draw an X where the orbital velocity of the planet would be fastest. It's going to be here where it's closest. Fastest here, slowest there, but fastest there. Okay? And then the last one looks like this. We're going to do the distance between the foci. You measure that there. 1.4. And then the length of the major axis is this. I got, looks like 10.0 cm. And then the eccentricity, if I do that math, 1.4 divided by 10.0 equals that. Now, it's exactly that. Notice there's infinite zeros there. So, to express it to the third decimal place, so thousandths, you got to write the 0 in there. Have to do that. It will be wrong if you don't. Be careful. Okay, and then 20 says, what is the eccentricity of Mercury? So I have to go here. Mercury is here. Eccentricity is here. 0.206. 0.206. Okay, which is more elliptical. Ellipse above or the orbit of Mercury. More elliptical. Again, less like a circle, more like a flat oval, the higher the number. So this number and this number is what we're comparing. The higher number is this one. This one's more elliptical, so orbit of Mercury. Okay? So, that's pretty thorough. Go back if you need to check any of this. Know these concepts here. Doesn't jump out at you. It will require some studying. So, I'm Mr. Gazda for all the folks at Gazdonian Productions. Thanks for watching.